Across the outer solar system, Uranus is surrounded by a strange family of moons. Some are bright with ice, others scarred by ancient impacts. But one of them stands out immediately: Oberon. From a distance, this distant moon looks darker than the others, as if its surface has been slowly swallowed by shadow. Sunlight that strikes Oberon seems to vanish rather than reflect, making it the darkest of Uranus's major moons. But that raises a question. Why would a world made largely of ice appear so dark? Is its surface coated with ancient cosmic dust drifting through the Uranian system? Could radiation from deep space be slowly altering its frozen crust? Or do the enormous craters and towering cliffs across Oberon hide a far older and more violent story? Because this distant moon may be more than just a quiet frozen world. Its battered surface records billions of years of impacts, geological fractures, and cosmic processes that shaped the outer solar system. And somewhere within that history may lie the answer to why Oberon looks so different from its neighboring moons. Before we begin exploring this mysterious world, subscribe to Theories Before Sleep, where we quietly explore the universe's most fascinating mysteries. Tonight, we travel to the dark moon of Uranus. Long before astronomers began studying the outer planets with powerful telescopes, the region around Uranus was completely unknown. For most of human history, Uranus itself was invisible to the naked eye, appearing only as a faint point of light among thousands of distant stars. It wasn't until 1781 that the planet was officially discovered by the astronomer William Herschel, opening a new chapter in our understanding of the solar system. But the discovery of Uranus was only the beginning. Over the following decades, astronomers began to realize that Uranus was not alone. Orbiting this distant blue planet was a collection of moons, strange icy worlds that existed in a region of space where sunlight is weak and temperatures are unimaginably cold. Among these moons was Oberon. Oberon was discovered in 1787 by the same astronomer who found Uranus. Using one of the most powerful telescopes of the time, Herschel identified two moons orbiting the distant planet. One of them was Titania. The other was Oberon. Even through the limitations of 18th century telescopes, it was clear that these moons were substantial worlds. They were not tiny, irregular rocks like many small moons in the solar system. Instead, they were large, spherical bodies shaped by gravity and composed largely of ice and rock. But despite being known for centuries, Oberon remained mysterious. Unlike the moons of Jupiter and Saturn, which were later explored by numerous spacecraft missions, Uranus and its moons have been visited only once. In 1986, NASA's Voyager 2 spacecraft flew past the Uranian system, capturing the first, and so far only, close images of these distant worlds. For Oberon, that brief flyby provided humanity's first real glimpse of its surface. What Voyager revealed was a landscape that looked ancient and silent. Oberon appeared heavily cratered, its surface scarred by countless impacts that had accumulated over billions of years. Huge circular basins dotted the moon, some stretching hundreds of kilometers across. Between these craters were dark plains and rugged terrain that seemed to have changed very little since the early history of the solar system. But one feature stood out immediately. Oberon was darker than expected. In the outer solar system, many moons are covered in bright water ice. Some, like Saturn's moon Enceladus, reflect nearly all the sunlight that strikes them. Their surfaces appear brilliant white, shining against the darkness of space. Oberon, however, was different. Its surface reflected far less light than similar icy moons. Instead of appearing bright and reflective, Oberon looked muted, almost charcoal grey in places. The moon seemed to absorb much of the sunlight reaching it. This raised an important question for planetary scientists. If Oberon is made largely of ice, why does it appear so dark? To understand that mystery, we first need to understand the environment in which Oberon exists. The Uranian system lies almost 3 billion kilometers from the Sun. At this distance, sunlight is roughly 400 times weaker than it is on Earth. Even at midday on Oberon, the Sun would appear little brighter than a star seen from our planet. Temperatures here are extraordinarily low. The surface of Oberon averages around minus 200 degrees Celsius. At such temperatures, water behaves more like solid rock than ice. It becomes incredibly hard, forming a rigid crust that can survive for billions of years without melting. But Oberon is not composed of ice alone. Like many moons in the outer solar system, Oberon is believed to be made of a mixture of water ice and rocky material. This mixture gives the moon a density that is higher than pure ice, but lower than that of rocky planets. Inside, Oberon likely has a layered structure. The outer shell is thought to be a thick crust of frozen ice and rock fragments. Beneath that may lie a partially differentiated interior where heavier materials have sunk toward the center. At the very core of the moon may exist a dense region of rocky material left over from its formation. However, unlike some other icy moons, Oberon does not appear to have strong internal activity today. Moons like Europa and Enceladus are constantly reshaped by internal heat, which drives geological activity and even creates subsurface oceans. Oberon, by contrast, seems relatively quiet. Its surface is old, very old. The vast number of craters across Oberon tells scientists that the moon has not experienced widespread resurfacing for billions of years. If geological processes were actively renewing the surface, many of those ancient craters would have been erased or buried. Instead, the landscape has remained largely unchanged since the era when the planets were still forming, and that ancient surface may hold the key to Oberon's darkness. Throughout the history of the solar system, small fragments of rock and dust have continuously drifted through space. Some of these particles originate from comets. Others come from collisions between asteroids or distant moons. Over millions and billions of years, this material slowly settles onto planetary surfaces. On Oberon, where there is no atmosphere and almost no geological activity, this dust remains where it lands. Layer after layer accumulates across the frozen landscape, gradually altering the moon's appearance. This cosmic dust is often dark in color. Many of the particles contain carbon-rich compounds and other materials that absorb sunlight rather than reflect it. As these particles settle onto Oberon's icy surface, they slowly darken the moon over time. The process is extremely slow. A single layer of dust may take millions of years to accumulate, but over billions of years, the effect becomes noticeable. The once bright icy surface becomes muted, darker, less reflective. Yet cosmic dust may not be the only factor influencing Oberon's appearance. Radiation also plays a role. Even though Uranus lies far from the Sun, the environment around the planet is not completely calm. Charged particles trapped within Uranus's magnetic field occasionally interact with its moons. These particles can alter the chemical structure of surface ice, gradually transforming it into darker compounds. This process, known as space weathering, occurs throughout the solar system. On airless bodies like the Moon or Mercury, space weathering slowly darkens exposed rock over time. On icy worlds like Oberon, similar processes may modify frozen materials, producing darker chemical residues on the surface. Combined with billions of years of micrometeorite impacts and cosmic dust accumulation, these effects can dramatically alter the color and brightness of a moon. But Oberon's story does not end with dust and radiation. Another important factor shaping its surface is impact history. The outer solar system is filled with small objects, remnants left over from the formation of planets. Over time, many of these objects collide with moons like Oberon, leaving behind enormous craters. Some of these impacts release tremendous energy. When a large object strikes the surface, it excavates deep layers of material from beneath the crust. Ice and rock from below the surface are blasted outward, forming bright rays around the crater. Interestingly, many of Oberon's largest craters appear to have brighter material around them. This suggests that beneath the dark outer layer lies fresher ice that has not yet been altered by cosmic dust or radiation. When impacts expose this material, it reflects more sunlight, creating a striking contrast against the darker terrain. These bright crater rays are like windows into Oberon's past. They reveal that the moon's darkness may be only skin deep, a thin coating that accumulated over billions of years, while the interior remained largely unchanged. But perhaps the most dramatic features on Oberon are not its craters, they are its cliffs. Voyager 2 images revealed enormous fractures running across the moon's surface. Some of these cliffs rise several kilometers high and stretch for hundreds of kilometers across the landscape. One of the largest of these structures is a massive cliff known as Rupes Oberon. It towers nearly 6 kilometers above the surrounding terrain. To put that into perspective, Mount Everest, the tallest mountain on Earth, rises about 8.8 kilometers above sea level. Oberon's cliffs are comparable in scale, carved into a frozen world nearly 3 billion kilometers from the Sun. These enormous fractures suggest that Oberon's interior may once have been more active than it appears today. At some point in the distant past, the Moon likely experienced internal expansion. As its interior warmed slightly, perhaps due to radioactive elements within the rock, it may have caused the outer crust to crack. These cracks spread across the surface, forming the gigantic cliffs we see today. Over time, the Moon cooled again. Geological activity slowed, and Oberon settled into the quiet, frozen state we observe today. But despite its silence, Oberon still carries the scars of its long history. Every crater, every fracture, every darkened plain tells part of a story that began billions of years ago, when the planets were young and the solar system was far more violent than it is today. And somewhere within that ancient record lies the explanation for why this distant moon appears darker than its neighbors. To uncover that answer, scientists must continue studying the complex interactions between ice, dust, radiation, and time. processes that slowly transform worlds across the solar system. Because even in the cold, distant shadows of Uranus, the forces that shape planets and moons are always at work. When Voyager 2 swept past Uranus in January of 1986, humanity saw Oberon up close for the very first time. Until that moment, Oberon had only been a faint point of light in telescopes on Earth. Even the most powerful instruments could reveal almost nothing about its surface. It was simply known as one of Uranus's outer moons, orbiting far from the planet in cold darkness. But the Voyager spacecraft changed that. As the probe approached the Uranian system, its cameras began capturing detailed images of the moons surrounding the planet. One by one, these distant worlds revealed their surfaces for the first time in human history. Titania, Miranda, Ariel, Umbriel, and finally, Oberon. What the spacecraft saw surprised scientists. Oberon appeared rugged, ancient, and heavily cratered. Compared to some of the other moons of Uranus, its surface looked far older and less geologically active. There were no vast, smooth plains formed by recent resurfacing. There were no signs of cryovolcanic flows like those seen on other icy worlds. Instead, Oberon looked like a place that had been shaped mostly by time and impacts. Large craters dominated the landscape. Some stretched more than 200 kilometers across, their circular rims standing tall above the surrounding terrain. Many of these craters had central peaks rising from their interiors. Mountain-like structures formed when the surface rebounded after the enormous force of an impact. These peaks reveal something important about Oberon's surface. Although the moon appears rigid today, the material making up its crust must have behaved differently during the moment of impact. When a large object strikes an icy moon, the energy released is so great that the surface temporarily behaves almost like a fluid. The crust compresses, melts, and rebounds before freezing again into solid, rock-hard ice. Over billions of years, countless impacts like these have sculpted Oberon's surface. Some of the craters are extremely old. Their edges are worn and softened by time. Others appear sharper and more recent, suggesting that impacts continued long after the moon first formed. But among the many craters scattered across Oberon, a few stand out for their unusual appearance. These craters are surrounded by bright rays. Unlike the darker terrain that covers much of the moon, these rays reflect significantly more sunlight. They form patterns of streaks that extend outward from the crater for hundreds of kilometers, almost like frozen explosions preserved on the surface. These bright rays are thought to be made of fresh ice. When a large asteroid or comet strikes Oberon, it blasts material from deep beneath the surface into space. Some of this material falls back down around the crater, forming a ring of debris. Because this ice has only recently been exposed, it has not yet been darkened by cosmic dust or radiation. As a result, it appears much brighter than the surrounding terrain. These bright crater rays offer an important clue. They suggest that the darkness covering Oberon is not uniform throughout its crust. Instead, the dark material likely exists mostly on the surface, forming a thin layer that has built up over billions of years. Beneath that layer lies fresher, brighter ice. This observation supports the idea that Oberon has been slowly accumulating dark material from space. But where exactly does that material come from? One possible source is the vast reservoir of dust that fills the outer solar system. Far beyond the orbit of Neptune lies a region known as the Kuiper Belt. This distant zone contains countless icy bodies, remnants left over from the formation of the planets more than 4 billion years ago. Occasionally, collisions between these objects send fragments drifting inward toward the Sun. Some of this debris eventually reaches the region around Uranus. Over enormous stretches of time, these particles settle onto the surfaces of the planet's moons. Each grain of dust may be microscopic, but collectively, they form a dark coating across the landscape. Another possible source of dark material comes from within the Uranian system itself. Uranus is surrounded by a complex network of rings and small moons. Collisions between these bodies can produce clouds of debris that spread throughout the system. Some of that debris may eventually fall onto Oberon. Because Oberon orbits far from Uranus compared to the planet's inner moons, it may accumulate material differently than its neighbors. This difference could help explain why its surface appears darker. But dust alone may not fully account for the moon's appearance. Scientists also suspect that radiation plays an important role. Although Uranus has a weaker magnetic field than Jupiter or Saturn, it still traps charged particles around the planet. These particles occasionally interact with the surfaces of the moons, altering their chemical structure. When radiation strikes water ice, it can break molecular bonds and trigger chemical reactions. Over time, these reactions can create darker compounds within the ice. The process is slow but relentless. Without an atmosphere or active geology to renew the surface, these changes accumulate over millions and billions of years. On Oberon, the result may be a gradual darkening of the crust. Yet Oberon's story is not just one of passive change. Evidence on its surface suggests that the moon may once have experienced internal forces capable of reshaping its landscape. Some of the most dramatic features discovered by Voyager were enormous fractures cutting across the terrain. These fractures appear as gigantic cliffs and scarves, steep walls where the surface has split apart. In some places, the cliffs rise several kilometers above the surrounding plains. Such features indicate that the moon's crust once experienced powerful stresses. One likely explanation involves the freezing of internal water. Early in its history, Oberon may have contained a partially molten interior. As the moon cooled over time, any liquid water trapped beneath the surface would have gradually frozen. Water expands when it freezes. If this process occurred within Oberon's interior, it could have forced the outer crust to stretch and crack. The resulting fractures would create the enormous cliffs and valleys we see today. This kind of geological activity may have happened billions of years ago, long before the Voyager spacecraft arrived. Today, Oberon appears geologically quiet. There are no signs of active eruptions or recent tectonic movement. The cliffs and craters stand frozen in place, preserved by the extreme cold of the outer solar system. But despite its quiet appearance, Oberon still holds many unanswered questions. One of the most intriguing mysteries concerns the moon's internal structure. Based on its density, scientists believe Oberon contains a mixture of rock and ice in roughly equal proportions. This composition suggests that during its formation, the Moon incorporated material from both icy and rocky regions of the early solar system. Over time, gravity may have caused the heavier rock to sink toward the center, forming a dense core. Surrounding that core could be a thick mantle of ice and frozen water. Some models even suggest that a thin subsurface ocean may once have existed between these layers. If such an ocean formed early in Oberon's history, it would likely have frozen long ago as the Moon cooled. Still, the possibility that liquid water once existed within Oberon raises fascinating questions about the evolution of icy moons throughout the solar system. Many of the most interesting worlds beyond Earth, including Europa, Enceladus, and Titan, contain hidden oceans beneath their icy surfaces. While Oberon does not appear to have an active ocean today, its early history may have included a similar phase. If so, the cracks and cliffs visible on its surface could be the frozen remains of ancient geological activity driven by internal heat. Understanding this history could help scientists learn more about how icy moons form and evolve around giant planets. But to fully solve the mysteries of Oberon, future exploration will be necessary. Voyager 2 captured only a portion of the Moon's surface during its flyby. Large regions remain unseen, hidden on the far side of the Moon. A future spacecraft mission to Uranus could map Oberon in much greater detail. High-resolution images could reveal subtle surface features invisible in the Voyager data. Instruments designed to analyze the Moon's composition could identify the exact materials responsible for its dark appearance. Radar systems might even detect structures beneath the surface, providing clues about the Moon's internal layers. Until such missions are launched, Oberon will remain one of the least explored large moons in the solar system, a distant world orbiting silently in the cold shadows of Uranus, a place where ancient impacts, cosmic dust, and frozen geological forces have combined to shape a landscape unlike any other. And perhaps somewhere on that dark, cratered surface lies the final answer to why this mysterious moon reflects so little light in the far reaches of space. If you were standing on the surface of Oberon, the universe would look very different from what we see on Earth. The sky would be permanently black, even during the brightest part of the day. The sun, nearly 3 billion kilometers away, would appear as a brilliant star rather than the blazing disk we know. It would still cast shadows across the frozen landscape, but the light would be faint and cold. Above the horizon, dominating the sky, would be Uranus. From Oberon's surface, the giant planet would appear enormous. Many times larger than the Moon appears from Earth. Its pale blue atmosphere would glow softly in the dim sunlight, wrapped in subtle bands of clouds and faint storms. But Uranus would not look like the planets we usually imagine in space illustrations, because Uranus is tilted dramatically on its side. Its axis leans at an angle of nearly 98 degrees relative to its orbit around the Sun. This means that the planet essentially rolls around the Sun rather than spinning upright like Earth or Mars. For the moons orbiting Uranus, including Oberon, this extreme tilt creates a strange and unusual environment. As Uranus travels around the Sun during its 84-year-long orbit, its moons experience extreme seasonal changes. For decades at a time, one hemisphere of the Uranian system is bathed in continuous sunlight, while the other remains in near total darkness. These seasons are far longer and more dramatic, than anything experienced on Earth. Oberon completes one orbit around Uranus every 13.5 days. During that time, the Moon remains locked in a gravitational embrace with the planet. Like Earth's moon, Oberon is tidally locked, meaning the same side always faces Uranus. As a result, one hemisphere of Oberon constantly looks toward the giant planet, while the opposite side faces outward toward deep space. This gravitational relationship affects many aspects of the Moon's environment. For example, the hemisphere facing Uranus may experience slightly different radiation conditions compared to the far side of the Moon. Charged particles trapped within Uranus's magnetosphere can interact with the surfaces of the inner moons more strongly, gradually altering their chemical composition. But Oberon's orbit places it farther away from Uranus than the other major moons. Because of this distance, the influence of the planet's magnetic environment is weaker here than it is closer to Uranus. The Moon spends much of its orbit outside the densest regions of the magnetosphere. This difference may help explain some of the unique characteristics of Oberon's surface. While moons closer to Uranus experience more intense radiation effects, Oberon's surface appears to be shaped more strongly by impacts and cosmic dust. Over billions of years, the Moon has collected countless craters from collisions with asteroids and comet fragments. These impacts record the violent history of the outer solar system, a time when planetary debris was far more common than it is today. One of the largest craters discovered on Oberon is Hamlet crater. This enormous basin measures more than 200 kilometers across. Its rim rises sharply above the surrounding terrain, and its interior contains a prominent central peak formed during the rebound of the crust after impact. The energy released by the collision that created Hamlet crater would have been staggering. When a large asteroid strikes an icy moon at tens of kilometers per second, the energy released can equal millions of nuclear explosions. The surface material vaporizes instantly at the point of impact, blasting debris high into space before it rains back down across the surrounding landscape. Such impacts not only create craters, they can also excavate material from deep beneath the surface. This is why some of Oberon's craters reveal brighter ice around their rims and ejector fields. The collisions expose fresher layers that have not yet been darkened by billions of years of cosmic weathering. These bright areas contrast sharply with the darker plains that dominate much of the Moon's surface. But craters alone cannot explain all of Oberon's geological features. Scattered across the Moon are immense canyon-like structures created by tectonic forces. These features appear as long valleys bordered by towering cliffs, where the surface has cracked and separated. Some of these fractures extend for hundreds of kilometers across the Moon's surface. The existence of these tectonic structures suggests that Oberon once experienced internal changes strong enough to fracture its crust. One possible explanation involves the gradual cooling of the Moon's interior. When Oberon first formed billions of years ago, it likely contained heat generated by radioactive elements trapped within its rocky components. This heat may have caused portions of the interior ice to melt, forming pockets of liquid water beneath the surface. As the Moon slowly cooled over time, that water would have begun to freeze, and as water freezes, it expands, This expansion could have pushed outward against the surrounding crust, creating enormous stresses within the frozen shell. Eventually, the pressure would have become too great for the surface to contain. The crust cracked. Massive fractures opened across the landscape. The cliffs and valleys visible today may be the frozen remnants of this ancient expansion. If this process occurred early in Oberon's history, it may also explain why the moon's surface appears so old today. After the internal heat dissipated and the water froze completely, geological activity would have slowed dramatically. Without internal energy to reshape the surface, Oberon became a quiet world, frozen, stable, and largely unchanged for billions of years. But despite its apparent stillness, Oberon continues to interact with the surrounding environment in subtle ways. Microscopic particles from space constantly strike the moon's surface. These impacts occur at extremely high speeds, slowly grinding the crust into fine powder known as regolith. Over immense spans of time, this regolith layer grows thicker. Each tiny collision alters the structure of the surface grains, darkening and weathering them. Solar radiation, though faint at this distance, also contributes to these changes. Even distant cosmic rays, high-energy particles traveling through interstellar space, can interact with the moon's icy surface. The cumulative effect of these processes is known as space weathering. Unlike weathering on Earth, which involves wind, water, and chemical reactions in the atmosphere, space weathering occurs in a vacuum. It is driven by radiation, micrometeorites, and the slow accumulation of cosmic dust. On Oberon, these effects gradually transform the appearance of the surface. Bright ice becomes darker. Fresh impact scars slowly fade. The moon's landscape evolves, not through dramatic geological activity, but through the slow passage of cosmic time. And yet, even after billions of years, Oberon remains only partially understood. Voyager 2 captured images of roughly 40% of the moon's surface during its flyby. The rest remains largely unseen, hidden from our view by the geometry of the encounter. This means that entire regions of Oberon remain unexplored. There may be enormous structures, vast basins, hidden fractures, or unusual terrain that we have never observed. Future missions to Uranus could change that. Scientists have long proposed sending a dedicated spacecraft to explore the Uranian system in detail. Such a mission could map Oberon's entire surface, analyze its composition, and investigate its internal structure. Orbiters equipped with modern cameras and spectrometers could reveal details far beyond what Voyager was capable of observing. Radar instruments could probe beneath the icy crust, searching for hidden layers or structural variations within the moon. Gravity measurements could help determine whether Oberon contains a dense, rocky core or other internal features. These observations would not only help us understand Oberon itself, they would also deepen our knowledge of icy moons throughout the solar system, because worlds like Oberon represent a class of planetary bodies that may be common across the universe. Cold, icy, quiet worlds orbiting distant planets. Some may hide subsurface oceans. Others may record ancient histories of planetary formation and evolution. Oberon stands as one of the most mysterious of these worlds, a dark moon circling a tilted giant planet in the far reaches of the solar system, a place where time moves slowly and the landscape preserves the echoes of events that happened billions of years ago. And although we have glimpsed its frozen surface only briefly, the clues left behind by impacts, fractures, and cosmic dust hint at a story far more complex than its quiet appearance might suggest. To truly understand that story, we must continue exploring, not just Oberon, but the distant frontier where the outer planets and their moons wait in the cold darkness beyond Saturn. For most of its existence, Oberon has remained far from the warmth and activity that shape many other worlds in the solar system. At a distance of nearly 3 billion kilometers from the Sun, the environment surrounding Uranus is incredibly cold and quiet. Temperatures on Oberon's surface remain around -200 degrees Celsius, cold enough to freeze almost any known substance solid. In such an environment, change happens slowly, very slowly, yet despite the extreme cold and the absence of an atmosphere, Oberon's surface has not remained completely untouched. Over billions of years, subtle processes have continued to alter its frozen landscape. Some of these changes are so gradual that they can only be understood by examining the moon's surface features in detail. One of the most striking aspects of Oberon is the sheer number of craters scattered across its terrain. Craters are the scars of impacts, collisions with asteroids, comets, and fragments of planetary debris traveling through space at enormous speeds. These impacts occur throughout the solar system, but their effects vary depending on the environment of the world they strike. On Earth, for example, craters are quickly erased by erosion, volcanic activity, and the movement of tectonic plates. Rain, wind, and oceans gradually reshape the landscape, hiding the evidence of ancient collisions. But Oberon has no atmosphere. There is no wind, no rain, no flowing water. Without these forces to erase them, craters remain visible for billions of years. Each impact leaves a permanent mark on the moon's surface, creating a record of the solar system's violent early history. The size and distribution of these craters tell scientists important things about Oberon's past. Large craters tend to form during periods when the solar system contains more debris. Early in planetary history, collisions were far more frequent than they are today. The enormous basins scattered across Oberon likely formed during this ancient era of heavy bombardment, when leftover fragments from planetary formation were still roaming through space. Smaller craters formed later. As time passed and the number of wandering objects decreased, impacts became less common, but they never stopped entirely. Even today, tiny micrometeorites continue to strike the moon's surface, slowly grinding the crust into fine dust. This dust gradually spreads across the landscape, covering older features and subtly altering the moon's appearance. Yet among all the craters on Oberon, some display unusual characteristics that hint at deeper processes occurring beneath the surface. Many large craters show signs of bright material along their rims and ejecta blankets. These brighter regions stand out sharply against the darker background terrain. The contrast suggests that the dark coating covering much of Oberon's surface may be relatively thin. When an impact excavates deeper layers of the crust, it exposes fresher ice that reflects more sunlight. This ice has not yet been altered by radiation or coated with cosmic dust. Over time, however, These bright regions slowly darken. Dust settles onto the exposed ice. Radiation modifies the surface chemistry. Eventually, the fresh material becomes almost indistinguishable from the surrounding terrain. This process reveals something important about Oberon's environment. Although the Moon appears static and unchanged, it is actually part of a dynamic cosmic system. Even in the far reaches of the solar system, tiny particles and energetic radiation continue to shape planetary surfaces. But Oberon's history may include more than just impacts and cosmic dust. The massive cliffs discovered by Voyager too suggest that powerful internal forces once fractured the Moon's crust. One of the most impressive of these features is a towering escarpment that stretches across a large portion of the Moon's surface. This enormous cliff rises several kilometers above the surrounding terrain, forming a dramatic boundary between two regions of crust. Geologists refer to such features as tectonic scarves. They form when the crust of a planetary body splits and shifts due to internal stresses. On Earth, similar processes create faults and mountain ranges as tectonic plates move and interact. Oberon does not have tectonic plates like Earth, but it may have experienced internal expansion early in its history. When icy moons form, they often contain heat trapped within their interiors. Some of this heat comes from radioactive elements embedded in the rock. Other heat may originate from the energy released during the moon's formation. If enough heat accumulates inside an icy moon, portions of the interior ice can melt. Liquid water may form beneath the surface, creating subsurface oceans or pockets of liquid trapped within the crust. Over time, as the moon cools, this water eventually freezes again. But freezing water expands. If large volumes of water froze within Oberon's interior, the expanding ice would push outward against the crust. The resulting stress could cause the surface to crack and split apart. The giant cliffs observed on Oberon may be the frozen evidence of this ancient expansion. These fractures could have formed billions of years ago, during a period when the moon's interior was still warm enough to support liquid water. As the interior cooled further, geological activity gradually slowed. Today, Oberon appears geologically inactive. There are no signs of recent eruptions, cryovolcanic flows, or tectonic movements. The moon has entered a long period of stability, preserved by the extreme cold of the outer solar system. Yet its ancient fractures remain visible, towering above the surrounding terrain like frozen monuments to a distant past. Beyond the cliffs and craters, another subtle feature of Oberon's surface provides clues about its history. Some regions appear smoother than others. These smoother plains may represent areas where impact debris or landslides have gradually filled in older terrain. When large craters form, the walls of the crater can collapse over time, sending avalanches of material sliding down toward the crater floor. On a world with such low gravity, these landslides behave differently than they would on Earth. Oberon's gravity is only about 1/10 as strong as Earth's. This means that falling debris travels more slowly and spreads out over greater distances. As material accumulates across the landscape, it gradually softens sharp edges and fills shallow depressions. The result is a terrain that appears ancient but subtly modified by countless small events. Even the cliffs themselves may slowly change over time. Tiny impacts can weaken the edges of steep scarps. causing fragments of rock and ice to break loose and tumble downward. These small collapses accumulate at the base of the cliffs, forming slopes of debris that gradually alter the shape of the terrain. Although these changes occur over immense periods of time, they demonstrate that Oberon's surface is not entirely frozen in place. Instead, it continues to evolve at an incredibly slow pace. But perhaps the most intriguing question about Oberon is not how its surface changes today, but how it formed in the first place. Scientists believe that Oberon formed at roughly the same time as Uranus itself, more than 4 billion years ago. During this early period, the outer solar system contained a vast disk of gas, dust, and icy material surrounding the growing giant planets. Within this disk, small particles began to collide and stick together. Over time, these collisions created larger and larger bodies. Eventually, some of these objects grew massive enough for gravity to pull them into spherical shapes. These became the moons orbiting the giant planets. Oberon likely formed from this process within the disk surrounding Uranus. Because the disk contained both ice and rocky material, the resulting moon developed a mixed composition. This combination of rock and ice remains visible today in Oberon's density and internal structure. But the early solar system was not a peaceful place. Collisions between young planetary bodies were common, and some of these impacts may have significantly altered the moons of Uranus. It is possible that Oberon experienced large collisions during its early history, reshaping its surface and influencing its internal structure. Some scientists have even suggested that the extreme tilt of Uranus itself may have resulted from a giant impact early in the planet's formation. If such a collision occurred, it may have affected the entire Uranian system, potentially altering the orbits and compositions of the moons. Oberon may therefore carry the scars of events that shape the entire planet it orbits. Today, this distant moon continues its slow journey around Uranus, completing one orbit every 13.5 days. It moves through the faint sunlight of the outer solar system, its dark surface reflecting only a small fraction of the light that reaches it. From Earth, Oberon remains little more than a tiny point of light seen through powerful telescopes. Yet behind that faint glimmer lies an ancient world, one shaped by impacts, internal forces, and the slow accumulation of cosmic dust over billions of years. A world that still holds many secrets waiting to be discovered in the silent darkness beyond Uranus. When scientists look at Oberon, they are not simply studying another distant moon. They are reading a frozen record of the early solar system. Every crater, every fracture, every dark plane across Oberon's surface is a page in a story that began more than 4.5 billion years ago, a story written long before Earth even formed oceans. Unlike worlds that constantly reshape themselves through volcanoes, tectonics, or weather, Oberon has remained almost completely unchanged for billions of years, and because of that, it may be one of the most honest historians in the solar system. A surface that barely changed. Most planets and moons evolved dramatically over time. Take Earth. Its continents drift, oceans rise and fall, mountains erode, and volcanoes constantly reshape the surface. Even the moon, which appears frozen and lifeless, experienced large volcanic eruptions that flooded ancient impact basins with dark lava. but Oberon appears to have experienced very little resurfacing since its earliest days. This means that many of the craters visible today may date back to the late heavy bombardment, a violent period roughly 4 billion years ago when the young solar system was filled with debris. During that time, countless asteroids and comet fragments smashed into planets and moons. The scars from that era still remain on Oberon, the most cratered moon of Uranus. Among Uranus's 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, one stands out. Oberon. Its surface is the most heavily cratered of them all. Some craters stretch over 200 kilometers wide. To put that in perspective, a crater of that size could easily swallow an entire country. These enormous impact basins formed when massive objects collided with the moon at incredible speeds. Because Oberon lacks a thick atmosphere, nothing slows these incoming objects. They strike the surface directly, releasing energy equivalent to millions of nuclear explosions. The result is a landscape carved by violence. The strange bright crater floors. Yet despite the darkness of Oberon's surface, something unusual appears inside many craters. Bright material. In some of the largest impact sites, the crater floors glow faintly compared to the surrounding terrain. This puzzled scientists when the Voyager 2 spacecraft photographed the moon in 1986. Why would the interior of craters appear brighter than the rest of the moon? One possible explanation involves fresh ice. When a large asteroid strikes Oberon, it may punch through the darker surface layers and expose cleaner water ice buried beneath. This brighter ice reflects more sunlight. Over time, space weathering slowly darkens it again. But for a while, the crater shines like a window into the moon's interior. A layered moon. These bright craters hint at something deeper. Oberon may not be a simple block of rock and ice. Instead, it may have layers. Most planetary scientists believe Oberon formed from a mixture of water ice and rocky material, roughly in equal proportions. As the moon cooled after its formation, heavier rock likely sank toward the center, forming a dense core. Above it would lie a thick mantle composed largely of frozen water ice mixed with darker compounds. This internal structure may explain why certain impacts reveal brighter material beneath the surface. It is possible that the darker outer layer is relatively thin, and below it, Oberon may still hide enormous quantities of ancient ice. The giant craters of Oberon. Some of Oberon's craters are so large they dominate the moon's geography. One of the most famous is Hamlet crater, named after the tragic prince from Shakespeare's play. It stretches roughly 206 kilometers across. Its walls rise high above the surrounding terrain, and its interior contains complex ridges formed by the rebound of the surface after the impact. When such massive collisions occur, the ground behaves almost like a liquid for a brief moment. The surface collapses inward, then rebounds upward. This creates central peaks and terraces inside large craters. These structures are visible across many planetary bodies, including our own moon. The long fractures across the moon. But Oberon's surface is not defined only by impacts. Across its ancient plains run enormous fault valleys and fractures. Some stretch hundreds of kilometers across the moon. These features suggest that at some point in the past, Oberon's interior expanded. But how could a frozen moon expand? The answer may lie in water turning into ice. If Oberon once contained liquid water beneath its surface, freezing would cause that water to expand slightly. This expansion could crack the outer crust. Over time, these fractures widened into long valleys. These giant cracks may represent the moment when Oberon's interior froze solid billions of years ago. A possible ancient ocean. Some scientists believe that long ago, Oberon might have contained a subsurface ocean, not an ocean like Earth's seas, but a hidden layer of liquid water buried beneath the ice. Many moons in the outer solar system are thought to have had such oceans in the past. Even today, worlds like Europa and Enceladus still contain active subsurface seas. For Oberon, the evidence is far less certain. But the fractures across its surface suggest that internal changes once occurred. If an ocean did exist, it likely froze completely long ago as the moon cooled, leaving behind only the scars of its disappearance. The color of darkness. Another mystery remains. Why is Oberon darker than Uranus's other moons? Scientists suspect the answer involves space dust. Over billions of years, tiny particles from comets and distant collisions have drifted through the outer solar system. These particles slowly settled onto Oberon's surface. Unlike inner moons that may experience geological resurfacing, Oberon's surface remained exposed. Layer after layer of dark material accumulated, gradually turning the moon darker and darker. In a sense, Oberon has been collecting cosmic dust for billions of years. A world at the edge of Uranus's gravity, Oberon's position in the Uranian system also plays an important role. It is the outermost of Uranus's large moons, orbiting nearly 584,000 kilometers away from the planet. At this distance, Uranus's gravitational influence is weaker. This means Oberon experiences far less tidal heating compared to inner moons like Miranda or Ariel. Tidal heating occurs when gravitational forces stretch and compress a moon's interior. That friction generates heat. But Oberon, being far from Uranus, receives very little of this internal energy. As a result, its interior cooled early and remained frozen, which explains why its surface appears so ancient and unchanged. The silence of an untouched world. If you could stand on Oberon today, the landscape would feel eerily still. The sky would be almost completely black. The sun would appear tiny and distant. Uranus would hang above the horizon like a pale turquoise giant. And beneath your feet, the ground would be ancient beyond imagination. No wind, no water, no shifting continents, just frozen terrain marked by billions of years of cosmic history. A moon we barely know. Despite its importance, Oberon remains one of the least explored worlds in the solar system. The only spacecraft that has ever visited Uranus is Voyager 2, and it flew past in January 1986. The spacecraft captured only a limited set of images before continuing its journey into interstellar space. Those photographs remain our primary view of Oberon. Most of the moon's surface has never been seen in detail. Entire hemispheres remain almost completely unexplored, which means the mysteries of Oberon are far from solved. Future missions to Uranus. Today, scientists are pushing for a new mission to Uranus. Modern spacecraft equipped with advanced cameras, radar instruments, and spectrometers could reveal details far beyond what Voyager saw. Such a mission could map Oberon's entire surface, study its composition, search for signs of ancient internal activity, and perhaps finally answer the question that continues to intrigue astronomers. Why did this moon become the darkest world orbiting Uranus? A frozen archive of cosmic time Oberon may not erupt with geysers like Enceladus. It may not hide a vast ocean like Europa, and it may not display chaotic terrain like Miranda. But its value lies elsewhere. Oberon is a time capsule, a frozen archive preserving events from the earliest days of the solar system. Every crater is a reminder of ancient collisions. Every fracture tells a story about the moon's internal past. And every dark plane carries the silent memory of billions of years drifting through space. In the darkness at the edge of Uranus's kingdom, Oberon waits quietly, unchanged, unmoving, and almost completely unexplored. But someday, a new spacecraft may return. And when it does, the ancient historian of the Uranian system may finally reveal the full story written across its silent, shadowed surface. For most of human history, the outer moons of the solar system were thought to be simple frozen worlds, solid, silent, dead. Their surfaces, covered in ice and ancient craters, appeared unchanged for billions of years, and for a long time, scientists assumed that nothing interesting could exist beneath them. But over the past few decades, that assumption has slowly collapsed. Again and again, space missions have revealed something astonishing. Hidden oceans, vast dark seas of liquid water buried beneath thick layers of ice. Europa, Enceladus, Titan. Even distant dwarf planets have shown signs of subsurface oceans. And this discovery raises an intriguing question. Could Oberon, the darkest moon of Uranus, also hide a buried ocean beneath its frozen crust? A cold world, but not always frozen. At first glance, the idea seems impossible. Oberon is extremely cold. Orbiting nearly 3 billion kilometers from the Sun, temperatures on its surface average around minus 200 degrees Celsius. At those temperatures, water should be frozen as hard as rock. Yet temperature alone does not tell the whole story. Deep beneath the surface of many icy moons, hidden heat sources can keep water from freezing completely. In fact, scientists now believe that liquid oceans may be common throughout the outer solar system. The key question is not whether water exists. It almost certainly does. The real question is whether something could keep that water liquid. The ingredients for a subsurface. Ocean. To maintain a hidden ocean, 3 ingredients are typically required. First, water. Second, heat. Third, insulation. Surprisingly, Oberon may possess all 3. Water ice is abundant throughout the Uranian system. Spectral observations show that Oberon's surface contains large quantities of frozen water mixed with darker materials. But beneath that icy surface, the moon's interior likely contains even more water. When Oberon formed billions of years ago, it likely accumulated from icy debris orbiting Uranus. This material would have included vast amounts of frozen water. But ice alone cannot form an ocean. There must also be heat. Heat from the moon's birth. When moons first form, they begin extremely hot. The process of accretion, where dust and rock collide and merge, generates enormous energy. Every collision releases heat. Over time, this energy builds up inside the growing moon. In addition to that, radioactive elements trapped within the rock slowly release heat through radioactive decay. Elements such as uranium, thorium, and potassium generate warmth for billions of years. Even small amounts of these elements can keep a moon's interior warmer than its surface. For Oberon, scientists estimate that its interior may contain enough radioactive material to have melted some of the surrounding ice early in its history. If that happened, liquid water could have formed deep underground. The role of antifreeze. There is another factor that may help keep water liquid in such cold environments: salt, or more precisely, chemical impurities mixed within the water. When substances like ammonia or salts dissolve into water, they lower the temperature at which it freezes. This process is similar to how salt melts ice on winter roads. In the outer solar system, ammonia may play a particularly important role. Ammonia-water mixtures can remain liquid at temperatures far below the freezing point of pure water. If ammonia exists inside Oberon's interior, it could allow a subsurface ocean to survive even under extremely cold conditions. The evidence hidden in Oberon's surface. So far, no spacecraft has directly confirmed an ocean inside Oberon. But there are clues. Subtle signs written across the moon's surface. Earlier, we discussed the long fractures that stretch across Oberon's terrain. These massive valleys may have formed when the moon expanded. Expansion could occur if liquid water inside the moon froze and expanded, cracking the outer crust. But this process may not have happened all at once. It could have occurred gradually as a subsurface ocean slowly turned to ice. Each phase of freezing would slightly increase the moon's volume, creating stress fractures across the surface. In other words, those enormous cracks may be the fossil remains of a dying ocean. A layered interior. Planetary scientists often model Oberon's interior as a layered structure. At the center lies a rocky core. Surrounding that core is a thick mantle of ice and rock mixed together. Above that sits the outer crust we see today. If an ocean once existed, it would have formed between the mantle and the outer ice shell. This hidden ocean layer might have been tens of kilometers deep. But over billions of years, as Oberon slowly cooled, the ocean likely froze. Today, most models suggest that if any liquid water remains, it would exist only in very small pockets deep underground. Still, scientists cannot rule out the possibility entirely. Lessons from other moons. To understand Oberon's potential ocean, researchers often compare it with other icy moons. Take Titania, the largest moon of Uranus. Some models suggest Titania may still possess a thin subsurface ocean today. If Titania can maintain liquid water, perhaps Oberon could as well. But there is a crucial difference. Titania orbits closer to Uranus. That proximity means stronger gravitational forces. Those forces create tidal heating, which generates internal warmth. Oberon, however, lies much farther away, which means tidal heating is far weaker. Without this additional energy source, maintaining a liquid ocean becomes far more difficult. A frozen ocean? Because of this, many scientists believe Oberon's ocean, if it ever existed, has already frozen solid. But that does not make the story less interesting. When water freezes under high pressure deep inside a moon, it forms unusual structures, different types of ice. Some of these high-pressure ice phases are denser than normal ice and behave almost like rock. Inside Oberon, layers of exotic ice may exist, stacked deep beneath the crust. These strange forms of ice could preserve the memory of the Moon's ancient ocean. The mystery of internal activity. Another clue may come from Oberon's tectonic features. Some of the long valleys cutting across the Moon's surface appear relatively younger than the surrounding craters. This suggests that internal activity may have continued long after the Moon first formed. If true, that activity could have been driven by internal melting. Perhaps a partially liquid interior pushed against the crust, creating enormous cracks. Or perhaps pockets of liquid water slowly migrated through the ice. Without more detailed exploration, these possibilities remain uncertain. What future missions might discover. Right now, Oberon is one of the least studied major moons in the solar system. Voyager 2 provided only a brief glimpse during its flyby in 1986. Future missions could change everything. A dedicated Uranus orbiter could carry instruments capable of detecting hidden oceans. Magnetometers could measure subtle magnetic signals produced by liquid water beneath the surface. Radar instruments could probe the internal structure of the ice shell. Gravitational measurements could reveal whether the Moon's interior contains liquid layers. With modern technology, scientists could finally determine whether Oberon once held a hidden sea. Why this matters? You might wonder why a buried ocean on a distant moon matters at all. But hidden oceans are among the most exciting discoveries in planetary science. Where there is liquid water, there is potential for chemistry. And where chemistry exists, there may be the ingredients for life. While Oberon is probably too cold and inactive to support life today, studying its past could help scientists understand how oceans form and disappear across icy worlds. Each moon is a chapter in the story of water in our solar system. The silent ocean that may have been. Imagine Oberon billions of years ago. Beneath its icy crust, a dark ocean stretches around the moon's interior. Slow currents move through the water. Chemical reactions occur between rock and liquid. Above it, the ice shell slowly thickens as the moon cools. Eventually, the ocean begins to freeze, year after year, century after century, until finally, the last pockets of liquid disappear, leaving behind only fractures in the crust, silent scars marking where an ancient ocean once lived. Oberon today appears frozen and lifeless, but its surface may still carry the memory of a hidden sea. And until we return to the Uranian system with new spacecraft, the question will remain: did Oberon once hold a secret ocean beneath its ice? Or does that ocean still exist, waiting in darkness, far beneath the moon's silent surface? Among all the large moons orbiting Uranus, Oberon stands out for one striking reason: its darkness. Compared with its neighboring moons, its surface reflects less sunlight, giving it a dim, shadowed appearance even under the faint illumination of the distant sun. When astronomers first examined images of Oberon captured by Voyager 2 in 1986, they immediately noticed that its surface looked darker and more ancient than the other Uranian satellites. While moons like Ariel and Miranda displayed brighter terrains and signs of geological reshaping, Oberon appeared quiet, heavily cratered, and covered in a mysterious dark coating. This darkness raises an important question. What exactly is covering Oberon's surface? At first glance, one might assume that the Moon is simply made of dark rock. But detailed spectral studies reveal that Oberon's surface is actually composed largely of water ice, mixed with darker materials. The ice itself should be relatively bright, reflecting sunlight efficiently. Yet something has altered its appearance, giving the Moon a dull, charcoal-like tone. To understand why Oberon looks the way it does, scientists must examine the many processes that shape surfaces in the distant outer solar system. Far from the Sun, where sunlight is weak and temperatures are extremely low, even subtle forces can slowly transform the appearance of a moon over billions of years. One of the most likely explanations involves the accumulation of dark material from space. The outer solar system is filled with microscopic dust particles produced by comets, asteroid collisions, and the slow erosion of other distant bodies. Over immense periods of time, these tiny grains drift through space and eventually settle onto planetary surfaces. Because Oberon lies at the outer edge of the Uranian system, it may act almost like a cosmic dust collector. Unlike the inner moons of Uranus, which experience more gravitational disturbances and occasional resurfacing events, Oberon's surface has remained largely unchanged for billions of years. This means that layer after layer of dark cosmic dust may have gradually accumulated across its icy terrain. Each individual grain of dust is almost invisible. But over millions or even billions of years, these particles can build up into a thin coating that darkens the entire surface. This process is known as space weathering. Space weathering occurs when surfaces in space are exposed to radiation, micrometeorite impacts, and energetic particles from the Sun. These processes slowly alter the chemical structure of surface materials. On icy moons, space weathering can transform bright ice into darker, more complex compounds. Radiation breaks apart molecules and rearranges them into new chemical structures. Over time, these reactions may produce substances known as tholins, complex organic molecules that appear reddish or brownish in color. Tholins are believed to exist on many icy bodies throughout the outer solar system, including Pluto, Titan, and certain Kuiper Belt objects. If similar processes occur on Oberon, they could help explain the Moon's dark coloration. Another possibility involves material originating from Uranus itself. The planet's magnetic field, although unusual and tilted dramatically relative to its rotation axis, still traps charged particles that can bombard its moons. When energetic particles strike icy surfaces, they can chemically alter the ice, producing darker compounds over time. However, Oberon's distance from Uranus complicates this explanation. Because the Moon orbits far from the planet, the intensity of Uranus's magnetospheric radiation is weaker there compared with the inner moons. This means that radiation alone may not fully account for Oberon's darkness. Instead, scientists believe that a combination of several processes may be responsible. Cosmic dust may settle onto the surface. Radiation may chemically modify the ice. Micrometeorite impacts may churn and mix the surface materials. Together, these processes slowly transform bright ice into darker terrain. Over billions of years, even the slightest changes accumulate, gradually turning Oberon into the dim world we see today. Another intriguing clue lies in how Oberon's brightness varies across its surface. Observations suggest that the Moon's leading hemisphere, the side that faces forward along its orbit, may be slightly darker than the trailing hemisphere. This pattern is common among many moons in the solar system. The explanation involves the way moons move through space. As Oberon travels around Uranus, the leading side of the Moon effectively plows through the surrounding environment, encountering more dust particles and debris. These particles strike the surface and deposit their material there. Over time, the leading hemisphere accumulates more dark dust than the trailing side. This subtle asymmetry supports the idea that external material plays an important role in shaping Oberon's appearance. Yet even with these explanations, mysteries remain. For example, some impact craters on Oberon display brighter material within their interiors. When large impacts occur, they can blast away the dark surface layer and expose fresher ice beneath. These brighter crater floors suggest that the dark coating covering Oberon may actually be relatively thin. If that is true, the Moon's interior ice might be much brighter than the surface we see. This raises another fascinating possibility. Oberon's darkness may not reflect its true composition, but rather a superficial layer accumulated over time. In other words, the Moon we observe today may be wearing a kind of cosmic dust blanket. Impact events provide another piece of the puzzle. Every crater on Oberon represents a moment when an asteroid or comet collided with the Moon at enormous speed. These impacts can excavate material from deep beneath the surface, scattering it across the surrounding terrain. If the excavated material differs in composition from the surface layer, scientists can analyze these differences to infer what lies beneath. Some of Oberon's largest craters reveal brighter deposits, supporting the idea that the darker material primarily affects the outermost layer. Yet the origin of this dark coating remains uncertain. It may come from distant comets passing through the Uranian system. It may originate from collisions among small moons or debris rings surrounding Uranus. Or it may even come from the Kuiper Belt, a vast region of icy objects orbiting beyond Neptune. Tiny particles from these distant sources could drift inward over time and settle on Oberon's surface. Because the Moon's gravity is relatively weak, it cannot easily retain thick atmospheres or active geological systems that might remove such deposits. Once the dust lands, it tends to remain there indefinitely. This slow accumulation of external material could explain why Oberon appears darker than Uranus's inner moons. Closer moons like Ariel and Miranda show evidence of past geological activity, tectonic fractures, resurfacing, and possible cryovolcanism. These processes may have refreshed their surfaces, exposing brighter ice and removing older dark coatings. Oberon, by contrast, seems to have remained geologically quiet for much of its history. Without resurfacing events to renew its appearance, the Moon has simply continued collecting dust. Over billions of years, this has slowly transformed its surface into one of the darkest among Uranus's major satellites. But darkness does not mean simplicity. The chemical processes occurring within this thin surface layer may be surprisingly complex. Radiation interacting with ice and organic compounds can create intricate mixtures of molecules. These compounds may record the long-term interaction between Oberon and the surrounding space environment. By studying the composition of such materials, scientists hope to better understand how surfaces evolve in the outer solar system. future missions to Uranus could provide critical data to answer these questions. Modern spacecraft equipped with advanced spectrometers could analyze the chemical composition of Oberon's surface in far greater detail than Voyager 2 ever could. High-resolution cameras could map subtle variations in brightness and color across the Moon. These observations could reveal where dark materials accumulate, where fresh ice is exposed, and how the surface changes over time. Perhaps most importantly, they could reveal whether Oberon's darkness truly comes from external dust, radiation chemistry, or some deeper geological process. For now, Oberon remains a quiet and enigmatic world. Its dark surface hides a complex story shaped by cosmic dust, radiation, and ancient impacts. Each crater, each patch of shadowed ice, and each subtle change in color represents another clue in the puzzle. And somewhere within those clues lies the answer to one of the Uranian system's most intriguing mysteries. Why is Oberon the darkest moon of Uranus? The answer may lie not in a single cause, but in billions of years of subtle change, dust settling silently from space, radiation reshaping molecules, and impacts revealing flashes of brighter ice beneath the darkness. Together, these processes have transformed Oberon into a world of shadows, a silent moon coated in the history of the outer solar system. The Uranian system is unlike anything else in the solar system. Orbiting the pale blue planet Uranus are 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Each of these worlds is unique, shaped by its own internal history and its distance from the strange tilted giant they orbit. But among them, Oberon stands apart, not because it is the largest, not because it is the most active, but because it is the most ancient, the most distant, and the most mysterious. To truly understand Oberon, scientists often compare it to its neighboring moons, and when they do, a fascinating pattern begins to appear. A system of 5 worlds, the 5 major moons of Uranus, form a kind of miniature planetary system. Each moon varies in size, surface brightness, and geological history. From closest to farthest from Uranus, the moons are arranged like this: Miranda, Ariel, Umbriel, Titania, Oberon. And as you move outward through this system, something interesting happens. The moons gradually become older and less geologically active. Oberon sits at the very edge of this system, nearly 584,000 kilometers from Uranus. This distance plays a crucial role in shaping the moon's character. Miranda, the moon that was torn apart. At the innermost edge of the Uranian system lies Miranda, perhaps the strangest moon of them all. Miranda looks nothing like Oberon. Its surface is chaotic, covered with enormous cliffs, fractured terrain, and bizarre patchwork landscapes. One of its most famous features is Verona Rupes, a cliff that drops nearly 20 kilometers. If you stood at its edge, the drop would be several times deeper than the Grand Canyon. Scientists believe Miranda may have been partially shattered and reassembled in the distant past. Powerful tidal forces from Uranus likely heated its interior, allowing the moon to reshape itself through geological activity. Compared with Miranda, Oberon appears almost perfectly calm. While Miranda's surface looks violently rearranged, Oberon's terrain remains stable and ancient. Ariel, the bright and active moon. Moving outward from Miranda, we encounter Ariel, Ariel is one of the brightest moons in the Uranian system. Unlike Oberon's dark surface, Ariel reflects much more sunlight. This brightness suggests that Ariel's surface has been renewed more recently, possibly through cryovolcanism, eruptions of icy material rather than molten rock. Ariel's surface is marked by long valleys and smooth plains that appear younger than the heavily cratered terrain seen on Oberon. These features suggest that Ariel experienced internal heating long after its formation. In other words, Ariel may have remained geologically active while Oberon had already grown cold and quiet. Umbriel, the shadowed neighbor. Beyond Ariel lies Umbriel, a moon that shares some similarities with Oberon. Umbriel is darker than Ariel and appears more heavily cratered. But even Umbriel is not quite as dark or ancient-looking as Oberon. One of Umbriel's most unusual features is a bright ring-shaped crater called Wunder. Its center contains a striking patch of bright material surrounded by darker terrain. This feature suggests that impacts may expose cleaner ice beneath the surface. Oberon also contains craters with brighter interiors, hinting at similar processes. But overall, Umbriel's surface appears slightly less battered than Oberon's. Titania, the giant of Uranus. Next comes Titania, the largest moon of Uranus. Titania is significantly bigger than Oberon and shows evidence of internal geological activity. Its surface contains massive fault valleys that stretch across hundreds of kilometers. These valleys likely formed when Titania's interior expanded, cracking the crust. Some scientists believe Titania may still contain a subsurface ocean beneath its icy shell. If that is true, Titania could still hold pockets of liquid water deep inside. Compared with Titania, Oberon appears quieter. Although Oberon also displays fractures across its surface, they are fewer and older. Titania's geological features suggest it remained active longer than Oberon did. Oberon, the outer guardian. And finally, at the edge of the Uranian system, lies Oberon. Oberon is the second largest moon of Uranus, slightly smaller than Titania, but its location makes it unique. It orbits farther from Uranus than any of the other major moons. Because of this distance, it experiences far weaker tidal forces. Tidal forces occur when a planet's gravity stretches and compresses a moon as it orbits. This constant flexing generates internal heat. Moons that orbit closer to their planets experience stronger tidal heating. Miranda and Ariel, for example, were heavily influenced by these forces. Oberon, however, lies too far away for strong tidal heating to occur. Without that extra internal energy, its interior cooled relatively quickly. As a result, Oberon became geologically inactive earlier than the others. The most ancient surface. Because Oberon's interior cooled early, its surface has remained largely unchanged. The moon is now covered with ancient craters, some of which date back nearly 4 billion years. These craters preserve the memory of the early solar system. Many other moons have lost evidence of this period through volcanic activity or tectonic reshaping, but Oberon has preserved its history like a fossil. Its surface is a time capsule from the violent early days when asteroids and comet fragments constantly collided with planets and moons. Darkness at the edge. Another key difference between Oberon and the other Uranian moons is its color. Oberon appears noticeably darker. Scientists believe this may be because of its position in the Uranian system. Being farther away, Oberon may collect more cosmic dust drifting through space. Tiny particles from comets and distant collisions slowly settle onto the moon's surface. Over billions of years, this dust forms a dark coating. Inner moons may lose such material through geological activity or interactions with Uranus's magnetic environment, but Oberon remains exposed to the outer solar system, quietly gathering dust over time. A system, frozen in balance. Despite their differences, the 5 major moons of Uranus share a common origin. Scientists believe they formed from debris left behind after a massive collision early in Uranus's history. This impact may have tilted the planet onto its unusual sideways axis. The resulting debris disk eventually condensed into the moons we see today. Each moon then followed its own evolutionary path. Some remained active longer, others cooled quickly, and Oberon, sitting quietly at the outer edge, preserved the oldest landscape of them all. What Oberon teaches us. Comparing Oberon with the other Uranian moons helps scientists understand how planetary systems evolved. Distance from the parent planet, internal composition, tidal heating, impact history. All of these factors combine to shape each moon differently. Oberon represents the end of that evolutionary spectrum. It is the moon that experienced the least heating, the least resurfacing, and the least change. In many ways, it is the most pristine survivor of the Uranian system's early history, the unexplored moon. Yet despite its importance, Oberon remains one of the least explored moons in the solar system. The only spacecraft ever to visit Uranus was Voyager 2, which flew past in 1986. During that brief encounter, Voyager captured only a limited number of images. Large portions of Oberon's surface remain completely unseen. Modern spacecraft could reveal incredible new details, hidden valleys, unmapped craters, perhaps even subtle clues about the moon's internal structure. Until such a mission occurs, Oberon will remain an enigmatic world, known only through distant glimpses and scientific imagination. Among the moons of Uranus, Miranda is chaotic. Ariel is bright and youthful. Umbriel is shadowed and mysterious. Titania is massive and fractured. But Oberon is the ancient guardian at the edge of the system, quietly preserving the earliest history of Uranus and its moons. And somewhere within its frozen surface, the secrets of the Uranian system's past may still be waiting to be discovered. For nearly 4 decades, our knowledge of the Uranian system has come from a single brief encounter. In January 1986, the spacecraft Voyager 2 flew past Uranus, capturing the first, and so far the only, close images of its moons. The spacecraft had only a limited amount of time as it sped through the system, and because of the geometry of its trajectory, it could only photograph parts of each moon. For Oberon, the encounter lasted just a few hours, and yet, from those few hours, scientists gained the first real glimpse of a world that had remained completely unknown since its discovery in 1787 by the astronomer William Herschel. But the images returned by Voyager 2 were only the beginning. Large portions of Oberon's surface remain unseen. Its interior structure is still unknown, and many of the moon's most intriguing mysteries, its dark surface, its fractures, and the possibility of a hidden ocean in its distant past, remain unanswered. To solve these mysteries, scientists believe we must return to Uranus, and when we do, Oberon will be one of the most fascinating worlds to explore. Why Uranus has been neglected. Among the giant planets, Uranus has received surprisingly little attention. Jupiter has hosted numerous missions, Galileo, Juno, and others. Saturn was explored for more than a decade by the Cassini spacecraft. Even distant Pluto received a historic visit from New Horizons. But Uranus has only been visited once. Part of the reason lies in distance. Uranus orbits nearly 3 billion kilometers from the Sun, making missions there long and technically challenging. Another reason is timing. Voyager 2 happened to pass Uranus during a rare alignment of the outer planets, allowing the spacecraft to continue onward to Neptune. But since that flyby, no spacecraft has returned. For decades, Uranus remained a forgotten frontier. Now, that may soon change. The next generation of missions. In recent years, planetary scientists have begun proposing ambitious missions to explore Uranus in detail. The most widely discussed concept is a Uranus orbiter and probe mission. Unlike Voyager 2, which simply passed through the system, an orbiter would remain around Uranus for years, carefully studying the planet and its moons. Such a mission could carry advanced scientific instruments capable of mapping the surfaces of the moons with incredible detail. For Oberon, this would transform our understanding overnight. Instead of seeing only half of the moon's surface, scientists could finally map the entire world, and what they might discover could completely reshape what we know about the Uranian system. Mapping the hidden side. One of the most important goals of a future mission would be to photograph the regions of Oberon that Voyager 2 never saw. During the flyby, only about 40% of Oberon's surface was imaged in moderate detail. The rest of the moon remains largely unexplored. An orbiter equipped with modern cameras could capture images with far higher resolution than Voyager's instruments. Small geological features, such as landslides, fresh impact craters, and subtle tectonic structures, could finally be examined. These images could reveal whether Oberon's surface truly remained inactive for billions of years, or whether small episodes of activity occurred more recently. In planetary science, even tiny details can reveal enormous secrets. Studying Oberon's interior, understanding what lies beneath Oberon's icy surface, is another key objective. A spacecraft orbiting Uranus could measure tiny variations in the moon's gravitational field. These measurements can reveal how mass is distributed inside the moon. If Oberon contains a dense rocky core surrounded by layers of ice, those internal structures will subtly influence its gravitational pull. By studying these variations, scientists could reconstruct the moon's internal structure. Such measurements might even reveal whether any liquid layers still exist deep inside. If a subsurface ocean once existed or still survives, its presence might be detectable through these gravitational signals. Searching for hidden oceans. Another powerful tool for detecting subsurface oceans is magnetism. Some moons with hidden oceans generate small induced magnetic fields when they move through their planet's magnetic environment. Europa, one of Jupiter's moons, displays this behavior. If Oberon once possessed, or still possesses, a liquid ocean containing salts or conductive material, it might interact with Uranus's magnetic field in a similar way. A magnetometer on board a future spacecraft could measure these signals. Even subtle magnetic variations could reveal whether liquid water exists beneath the ice. Detecting such an ocean would dramatically change our understanding of Oberon's history. Analyzing surface chemistry. A new mission could also examine Oberon's surface composition in far greater detail. Voyager 2 provided only limited spectral data. Modern spectrometers could analyze the chemical makeup of the Moon's surface with incredible precision. These instruments could identify the presence of compounds such as ammonia, methane, or complex organic molecules. Understanding the chemistry of Oberon's surface would help scientists determine the origin of its dark coloration. Is the darkness caused by cosmic dust drifting through the Uranian system? Is it the result of radiation altering the surface ice? Or could it come from material emerging from the Moon's interior long ago? Spectroscopic measurements could finally answer these questions. Measuring the ice shell radar instruments could provide another powerful method for exploring Oberon. By sending radio waves into the surface and analyzing the reflections, scientists could estimate the thickness of the Moon's ice shell. Radar sounding has already been used successfully on Mars to study buried ice layers. Applied to Oberon, this technology could reveal whether the crust is uniform or layered. It might even detect buried structures such as ancient fractures or frozen pockets of liquid. These measurements could provide clues about the Moon's internal evolution. Investigating impact, history. Oberon's heavily cratered surface makes it an ideal laboratory for studying the impact history of the outer solar system. Each crater represents a collision that occurred sometime during the Moon's long history. By studying the sizes, shapes, and distributions of these craters, scientists can estimate how frequently impacts occurred over time. This information helps reconstruct the environment of the early solar system. For example, if Oberon's craters formed primarily during the late heavy bombardment, that would support theories suggesting that a dramatic increase in impacts occurred around 4 billion years ago. Studying Oberon could therefore help answer questions about planetary formation across the entire solar system. Observing the Uranian system. A mission to Uranus would not focus solely on Oberon. The spacecraft would also study the planet itself, its rings, and its other moons. But Oberon would play a crucial role because of its location at the outer edge of the system. From its distant orbit, Oberon may have experienced interactions with objects from the Kuiper Belt, the vast region of icy bodies beyond Neptune. Some of the craters on Oberon may have been created by these distant objects. By studying these impacts, scientists could gain insight into how Kuiper Belt objects move through the outer solar system. Preparing for the journey. Sending a spacecraft to Uranus is no small task. Because of the immense distance, the journey could take more than a decade. The spacecraft would need powerful instruments, long-lasting power sources, and the ability to operate far from the sun where solar energy is weak. But the rewards could be enormous. Exploring Uranus would open a completely new chapter in planetary science, and Oberon would be one of the key worlds awaiting discovery. A moon, waiting to be explored. Right now, Oberon remains one of the least understood large moons in the solar system. We know its size. We know it is dark and heavily cratered. We know that fractures cross its ancient surface. But beyond that, many questions remain unanswered. What lies beneath its ice? Did it once contain a hidden ocean? Where did its dark surface material come from, and how has it survived for billions of years with so little change? Only a new mission can answer these questions. Somewhere in the distant future, a spacecraft may arrive once again in the Uranian system. It will approach the pale blue planet, its rings glowing faintly in the darkness. And beyond those rings, orbiting silently at the edge of Uranus's gravitational domain, a dark moon will appear. Oberon, a frozen world that has waited billions of years to reveal its secrets. And when the next spacecraft finally turns its cameras toward that distant moon, humanity may discover that Oberon still has many stories left to tell. Far from the warmth of the sun, orbiting a pale blue giant nearly 3 billion kilometers away, Oberon moves silently through space. It is a quiet world, a frozen world, a world that has remained almost unchanged for billions of years. At first glance, Oberon might seem unremarkable compared to some of the more dramatic moons in our solar system. It has no towering geysers, like Saturn's moon Enceladus. It shows no chaotic, broken terrain like Miranda. It does not glow with the possibility of a vast subsurface ocean like Europa. Instead, Oberon appears calm, ancient, silent, and yet that silence may be exactly what makes it so important. Because sometimes the worlds that change the least are the ones that preserve the greatest secrets. Oberon is not just another moon orbiting Uranus. It is a record keeper of the early solar system. A survivor. From the beginning, more than 4.5 billion years ago, our solar system was a chaotic place. The planets had not yet settled into their modern orbits. Vast clouds of dust and ice surrounded the young sun, colliding and merging into larger bodies. Asteroids, comets, and protoplanets smashed into one another in a violent process that gradually formed the worlds we know today. During this time, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were still shaping the architecture of the outer solar system. Around Uranus, debris from these early events slowly gathered together. Over time, that debris formed the moons we see today. Oberon was born during this era of cosmic construction. Unlike some moons that later experienced intense internal heating and geological activity, Oberon appears to have cooled relatively quickly. This early cooling meant that its surface stopped evolving long ago, and because of that, Oberon preserved the scars of those ancient collisions. In other words, Oberon still carries the memory of the solar system's earliest days. A time capsule. In space, planetary scientists often refer to heavily cratered worlds as time capsules. These surfaces preserve a record of impacts stretching back billions of years. On Earth, such records are constantly erased. Plate tectonics recycles the crust, volcanoes reshape the surface, and erosion slowly destroys ancient structures. But on frozen moons like Oberon, time moves differently. Without weather, oceans, or tectonic activity, the surface remains largely unchanged. Every crater that forms stays visible for enormous periods of time. Some of the craters on Oberon may be more than 4 billion years old. That makes them among the oldest visible structures in the solar system. By studying these ancient features, scientists can reconstruct the history of impacts that shaped the outer planets. Each crater tells a story about the environment of the early solar system. How many objects were flying through space, how large they were, and how often collisions occurred. Oberon is therefore more than just a moon. It is a historical archive written across ice and rock. The story of planetary cooling. Oberon also helps scientists understand how planetary bodies cool over time. When moons first form, they often contain internal heat generated by radioactive decay and gravitational compression. This heat can drive geological activity, melting internal ice and reshaping the surface. But as billions of years pass, that heat gradually escapes into space. The moon cools, its interior freezes, and geological activity slows or stops entirely. Oberon appears to represent the later stages of this process. It likely experienced some internal activity early in its history, perhaps enough to fracture the crust or create subtle tectonic features. But eventually, its interior cooled to the point where large-scale geological change became impossible. Studying Oberon therefore provides insight into how icy worlds transition from active bodies into frozen relics. The outer edge of a planetary system. Another reason Oberon matters lies in its position. Among the 5 major moons of Uranus, Oberon orbits farthest from the planet. That distance places it at the boundary between the Uranian system and the outer solar system. Because of this location, Oberon may have been exposed to impacts from distant objects originating in the Kuiper Belt. The Kuiper Belt is a vast region beyond Neptune, filled with icy bodies, remnants from the formation of the solar system. Some of these objects occasionally travel inward. When they do, they can collide with planets or moons. If Oberon's craters were formed partly by these distant objects, then the moon may preserve evidence of how the outer solar system evolved. In this way, Oberon connects 2 regions of space, the Uranian system and the distant frontier beyond Neptune. Understanding icy worlds. Oberon is also part of a much larger family of icy moons throughout the solar system. From Jupiter's Europa to Saturn's Enceladus and Neptune's Triton, many moons contain vast amounts of frozen water. Some of these worlds even harbor hidden oceans beneath their surfaces. By comparing Oberon to these moons, scientists can learn how different environments influence the evolution of icy worlds. Why do some moons remain active for billions of years while others freeze solid early in their history? Why do some develop subsurface oceans while others do not? Oberon may hold clues to these questions. Its relatively inactive interior suggests that tidal heating plays a crucial role in sustaining geological activity. Moons closer to their parent planets experience stronger gravitational forces, generating internal heat. But Oberon lies far enough away that those forces are weak. Without tidal heating, the moon cooled quickly. This comparison helps scientists understand how distance from a planet shapes the evolution of its moons. A world yet to be discovered. Despite its scientific importance, Oberon remains one of the least explored major moons in the solar system. The images captured by Voyager 2 in 1986 showed only part of its surface. Much of the moon remains unseen. We do not yet know what lies on the far side. There may be enormous impact basins hidden there, unknown tectonic features, or geological structures never before observed. Modern spacecraft equipped with advanced instruments could transform our understanding of this distant world. High-resolution cameras could map every crater and valley, spectrometers could analyze the surface chemistry in detail, radar systems could probe beneath the ice, and magnetometers could search for signs of hidden liquid layers deep underground. Such discoveries could reveal whether Oberon once possessed a subsurface ocean, or perhaps still contains traces of one today. Why exploration matters. Exploring distant worlds like Oberon is about more than curiosity. Each new discovery helps scientists understand the broader story of how planetary systems form and evolve. The outer solar system contains many icy bodies similar to Oberon. By studying one of them closely, researchers can apply that knowledge to dozens of other worlds. Oberon therefore acts as a kind of natural laboratory. It allows scientists to test theories about planetary formation, internal structure, and surface evolution. In doing so, it helps us better understand not just Uranus and its moons, but the entire solar system. A quiet world with a powerful story. From a distance, Oberon might appear to be nothing more than a dark, frozen sphere orbiting a distant planet. But appearances can be deceptive. Beneath its quiet surface lies a story billions of years in the making. A story about the birth of moons, about ancient impacts that reshaped entire worlds, about the slow cooling of icy interiors, and about the evolution of the outer solar system. Every crater on Oberon is a chapter. Every fracture is a sentence. And every dark plane is a page in the cosmic history book of our planetary neighborhood. Somewhere in the future, a new spacecraft may arrive in the Uranian system. It will pass through the planet's faint rings and begin exploring the moons that circle this distant giant. When its cameras finally turn toward Oberon, humanity will see that world with clarity for the first time. The ancient moon that has waited silently for billions of years will reveal its hidden landscapes. And in those landscapes, scientists may discover answers to questions that have lingered since the dawn of planetary exploration. Because Oberon is not just a distant moon. It is a witness to the earliest chapters of our solar system. And its story has only just begun to be understood.